Hi everyone, in this tutorial I will show you how to solve set of differential equation using an Excel sheet. So I will be using an analytical approach to solve these differential equations. For this particular video tutorial I have used the example of diffusion. Here I have defined two chambers, inside chamber and outside chamber. So there is a concentration of C in the inside chamber and C out in the outside chamber. The outside chamber is exposed to air, so the things in the outside chamber can diffuse to open air with the diffusion coefficient of K dash, and from diffusion can occur from inside to outside with the diffusion coefficient of K double dash. And these are the differential equations. This is a pretty standard differential equation for diffusion, where change in the concentration is proportional to the concentration difference from where the diffusion is occurring. And to solve this differential equation analytically, we need to go to a very small time scale. And if we go to very small time scale of dt, then we can rewrite this differential equation again in this form. So here, instead of writing dt, I'm writing C in at t is equal to t minus C in at t is equal to t minus dt. So here I'm saying that if I assume a very small time scales, for example 1 millisecond or 10 millisecond, then I can just assume that dc is just a subtraction of C at a forward time minus C at present time. And similarly, instead of writing C in, I can say that C in is something at the backward time. So I can write these equations like this. Now to solve this equation, I need to define K double dash. So let's call K double dash is equal to 1 and K dash is equal to 2. So these are the arbitrary numbers. You can change it later if you like. And then let's define dt, and dt is equal to 0.01 here. So let me write 0.01. Now what I'll do is I'll first define t. So t, so I'll say t, and t is equal to 0 in the beginning. So at t is 0, t is 0. So let me, and then let's define C in and then C out. So let me center them. Yes. So now C in, let's assume the initial concentration is 100 in the first chamber and 100 in the outside chamber. And now at after time dt, the time will be dt. So that what we call is that t plus dt, and because dt is constant, so I need to put dollar sign with this number, so that will ensure that dt is not changing if I try to grab this series down. Now C in, so for C in I will use the formula which is defined here. Let me grab the differential equation here. So I'll say C in is equal to C in at t is equal to t minus dt minus dt. So this is dt, and I put dollar sign again, and then into K dash double dash. So K double dash, again I put a dollar sign here, and then into C in minus C out. And now here I'm not putting a dollar sign on C in and C out, because the C in and C out are not constant and they will change with the time. So I'll put enter here. And now here C out, let me grab the equations here, and I say C out is equal to C out at t minus dt, and then minus dt, which is constant, so I put dollar sign here, and then into K dash is constant, so I put dollar sign here, and then into C out. So C out is not constant, so it will be C out here. I'll press enter. So now this is what I have. Now all I need to do is grab these three numbers and then drag them down. So I need to simulate for long time because I want to go to t infinity and see how does it go. So let's stop here, and you can see the concentration in both the columns are now approximately or very close to 0. So now if I go up, I can plot, and then this is a plot for C in and C out. But as you can see, this two curves goes to 0 because if you look in our model, the diffusion is happening from chamber to the open air, and open air is a sink, so everything will eventually evaporate and goes to air, so everything will be consumed, so concentration should go to 0. That means our model is working. However, we can see that we can vary the speed here by changing the diffusion coefficient. For example, now we have k double dash is equal to 1, so if I put k double dash is equal to 5, then the speed is much faster. And now if I put it slower like 0.5, then speed is slower. Like a dynamic model, so where I can change the numbers and I can see the results right away. And this is a simulation. So differential equation, I don't need to use the algebra or calculus to solve this. I'm just using a simple method to solve the differential equations and come up with the pattern, and with the parameters I can change the patterns here.